what's stopping me from falling over? You know, if I'm
Falling
standing
over, what's going to pull you?
well, gravity, apparently.
Gravity is a radial force. It's not a tangential force. There's nothing to pull you sideways.
So if gravity is a radial force, that means it should pull up just as much as it pulls down then, yes?
No, it's radial toward the center of mass of the object, not
And then
outside.
it stops pulling.
That is exactly what I'm saying. If it is pulling towards the center of the mass, it's pulling me down towards the Earth, yes? Because that's the center of the mass.
Right.
Well, then why don't I fall over if I'm at the equator?
Because it's pulling you toward the center. Every place on the Earth is pulling you toward the center of the Earth.
It's pulling me on that vertical plane down towards the center, but what about, why am I not falling over to the side if I'm standing on the equator?
Because there's nothing pulling you down. That's why. There's no tangential force pulling on you. There's only one force. That's a radial force pulling you toward the center. There's no other forces. The only other forces that are available are the Coriolis force.
Oh, really? What about magnetic forces? What about...
Yeah, but you're not made of iron, so you don't have any
It doesn't matter.
We're magnetic.
It doesn't matter. Neither is water. In fact, water is diamagnetic.
Mm-hmm.
So, okay. So great. So how do you explain that? There are many things, and for that matter, you can take multiple like neodymium magnets, and you can place them around like in a toilet paper tube. And we were always told that those magnetic fields in just iron core magnets are fixed. Well, if you place those around in a circle, and you put an object in the middle of it, you can actually those magnetic forces will actually cause a vortex and cause things to spin. Okay, so there are other forces.
I have no disagreement with that.
Okay, and there are any
in a circle is going to create a vortex.
Okay,
but that's not what happens when you're on the equator as a human being.
That yes.
I mean,
So there's no other force that's going to pull you. Is what I'm trying to answer. I'm trying to answer your question.
Your question
was, why don't I fall over? Because there's no force to make you fall over. There's only one force. That's a radial force. It's powerful enough to keep you there. Magnetic forces are inconsequential.
You're saying that something at the center of the globe is pulling every single person as if there's a string from their head straight through the center of their body and out the middle of their feet. And every single person across the entire globe is being pulled tightly to the very center. That's what you're saying, right?
Yeah. You know why? Because if I'm in New York City and I drop a pen from my desk, it's going to fall to the floor. If I go to Australia, the same thing's going to happen. If I drop it, it's going to hit the floor.
Beautiful. So now we're on the same page as far as that goes. But we're saying that doesn't it make 100 times more sense that the Earth is flat? What you're coming up with is the most fantastical idea ever that nobody can ever witness. No, NASA's flying around the planet. Why can't they show us this person who's upside down in Australia? Because it doesn't exist. It does exist if you're saying, well, in my perspective, I'm upright, and in their perspective, they're upright. Well, yeah, now you've made it exist. But if it cannot be filmed, it cannot be shown, it cannot be proven. It's just conjecture. It's a fantasy world.
Wait a minute, Jaron. Let's deal with your flat Earth. If I drop a pen from my desk, will it hit the floor on a flat Earth model?
Absolutely.
Yes, because it's denser than what it's going through. It's denser than the medium it's going through.
Everything
conversely,
what's denser? What's denser?
The pen is. The pen is. If I drop that same pen, depending on the pen, and I drop it into water, it's going to float, isn't it? Because, well, it could float, but not necessarily. But if it had enough displacement, it's going to float.
And a helium balloon.
So let's say we took your density model and we put it on a spherical Earth. Would it work the same in New York as it would be in Australia?
No, because our density model excludes gravity, and therefore we
Wait a minute. You just tried to explain to me why the pen falls. You said because it's denser.
Falls
Why
down.
does the density model work on a spherical Earth?
Because there is no where's the down.
Because there is no, because the spherical Earth would not allow for that to happen.
Why?
Okay. Because you would oh Jesus.
Well, it's like if you're saying that, so a pen from New York is going to fall, and you're saying in the flat Earth, does that allow for that to happen the same in every location? I'm confused by your question.
No. I'm just saying, what makes the pen fall in a flat Earth model? Bob said density. I said, okay, let's take that model and put it in a spherical Earth. will it apply? And he says no. I asked him why. He said Jesus.
Well, it's just,
I should have said God. I'm sorry.
No, I mean, but what he meant to say is, or I don't know.
I just want to jump in here real quick because the issue is that it doesn't work on a ball Earth because buoyancy and density, as far as I know of, is not a force that pulls things into a center. So on a flat Earth, we don't have a center to pull anything into. Things float up, things fall down. That's
right.
That's how things happen.
See, the problem here, guys, is that when you're envisioning a spherical Earth, Australia is at the bottom, and so somehow your intuition thinks that something's pulling objects that are in Australia down, away from the Earth because it's down. That's what your problem is, okay?
No,
that's not the way it works, okay? There are no other forces outside the Earth's gravity envelope there that are going to affect any object on the Earth.
If you think about flying, Bob, or Robert, from San Jose, California, and you fly down to the tip of South America, in your ball world, that plane is ending up upside down from where it started. Now you're going to say.
But no, Jared, I do not believe that because upside down is a relative term.
Okay, but it's relative to one person, so I agree with you. I was going to make a video that says, I can live on a ball and you can live on a ball, but we cannot live on a ball. Okay. You are describing your one perspective. You're saying, oh, I can explain away the fact that my plane has to go upside down by saying, to me, I stayed upright the whole time. I'm saying everyone else flying in a plane at that exact time also is going through that same thing. They can't all say, no, to me, I stayed flat. Well, you say, well, to me, I stayed flat. Well, that disproves it.
And additionally,
you can't do that.
And additionally,
look, you can't.
You're right.
Nobody can say anything about upside down or right side up because there is no place outside of the Earth to make such a measurement.
But we live on the Earth,
but we
and
can,
there's up
we
and
can
down.
emulate it. We can say, you're right when you say, Robert, when you say that it's a relative term, okay, you're absolutely right. But look at it this way. If I take a stick pin and I take a globe and I stick it on the bottom of the Earth into Antarctica, and then I take another pin and I stick it on the top of that globe, relative to each other, they're upside down from each other, yes? Would you agree with that?
Because
if you say upside down to each other, yes, I could agree to that. But you can't.
Well, that's what relative means. That's what relative means.
Wait. Jaron was saying that the guy that's in Argentina is upside down, and the guy that's in New York is right side up.
Right.
I'm not saying right side or upside down.
Well,
you can't do that, okay?
Why not take that
because
same
now you're
model
making distinctions. It's not relative anymore.
But it is.
When you put anywhere.
Because if you take a stick pin and you stick it in Argentina, and you take a stick pin and you stick it in New York on the globe, relative to each other, one is upside down or in opposite direction.
That's right. That's because you just hit the key phrase, relative to each other. That's not what Jaron said.
Well, I'm agreeing with you. Relative, because that's what relative
well, then you disagree with Jaron.
Robert, well, we do that a lot, actually. But, Robert, wherever you're at right now, if you were to look out at your horizon.
Hey, guys, can I interrupt you just for a second here? Okay. It's 11:45 where I'm at, okay, and that's in Pennsylvania in the northern hemisphere. Okay. And it's getting a little late for me, so I'd love to do this some other time as well, but let's give it 5 more minutes and then call it a night, okay?
Beautiful. Okay. And we appreciate you being here. And
we do. And Robert, we have nothing but the utmost respect for you. And granted, we have very different views on this, but it's great to be able to talk stuff like this out. And so there's no animosity here, but and we're very passionate about what we believe in, as are you. And you have encountered that same type of passion with the heliocentric model believers, I'm sure. So this is no stranger to us. It's no stranger to you. And believe me, it does not mean that we think any less of you. In fact, we think it's great that you're actually in here talking to us about it.
Good. Let me talk about something other than the flat Earth for a second, if that's okay with you guys, so we can end on a good note here.
Sure.
You were talking about the conspiracies of NASA and the conspiracies of modern science in general, and somebody threw around the word scientism at the beginning of the program, as a matter of fact. Mm-hmm. And what I find most interesting is that the whole understanding, the whole foundation of modern science today, especially physics and cosmology, is built on Albert Einstein, as you well know.
Yes.
And what we painstakingly tried to point out in our videos is this whole idea that ever since Copernicus, it's impossible for mankind to believe that the Earth could be fixed in the center of the universe, right? So they did these experiments, and I think you guys are familiar with these. You should be, if not. The Michelson-Morley experiment of 1887, yes. And yes. The Michelson-Gale experiment of 1925, and
yes.
And all the other interferometer experiments that were done. And just to close on a good note, I just want to point this out because I just love pointing this out. The whole idea of special relativity, Einstein's special relativity, it is such a joke because it was invented to answer these experiments that were done dozens and dozens of times that show the Earth wasn't moving.
Mm-hmm.
And so, you get this paradigm in your mind, well, that can't be. That just can't be. And if you read the literature on Einstein, the biographies, even the biographers say it. They say, well, the other solution to Michelson-Morley was that the Earth wasn't moving in space, but that just can't be. That's preposterous because we've all learned from Copernicus that the Earth has been moving, right? So, I just find it so hysterical that, was it, first of all, it was Henrik Lorentz in 1892 that came up with this theory of why Michelson's interferometer showed that the Earth wasn't moving. Yes. And Lorentz's bright idea was what, guys? Do you know what it was?
The transform?
Yeah, the Lorentz transform.
Yes.
That Michelson's apparatus was shrinking.
Right.
And the Earth was moving.
Yes. Yes, it's crazy.
Yeah, well, this is so ludicrous, and even Einstein didn't like that. I mean, he said, "Come on, Lorentz, there's no proof for electron shrinking."
Exactly.
But Einstein was stuck. He had no causal factor for the shrinking, and he needed the shrinking, otherwise he couldn't explain Michelson's experiment either. So he just said, "Well, when objects move, they just shrink," and he gave us no cause for it. As a matter of fact, there were some philosophers around that time that were saying that Einstein was violating the cause and effect rule of philosophy.
Well, yeah, and didn't Einstein also, according to his theories, as you increase speed or you move and you increase speed, like even towards the speed of light, things actually grow, right? Mass increases.
Yeah, well, he had to do that, and here's the reason why. Because if you say that the length contracts when an object moves, that means when it leaves point A and tries to go to point B, it's not going to get there in the same time because its length has contracted.
Exactly.
So you have to add time to it. That's why you have to add time dilation. And if the object isn't going to reach point B at the same time, that means the mass isn't going to be the same. Right. As it passes point B, so you have to increase the mass.
Exactly.
Yeah, you see that?
I love the experiment when they take the ladder and try to go across the ditch.
It's like a haunted house of mirrors.
Yes.
You have to increase the length, you have to dilate the time, and you have to increase the mass. All for what? So that we can keep the Earth moving when the experiment showed us it was fixed in space.
And yet it moves.
Yep, exactly. And
something strange in your neighborhood, who you gonna call? If there's something weird and it don't look good, who you gonna call? That's right. I ain't afraid of no ghost. You're seeing things running through your head. Who you gonna call? Ghostbusters. I ain't afraid of no ghost. You know, busting makes me feel good. I ain't afraid of no ghost.